charge better. If it is a more stable charge, what does that mean about its strength as a base? It'll be less basic. Okay? So we have to consider that when we look at this. So let's take a look at the pyridine, because we actually got an example with that one. So let's take a look. Here's our pyridine. One of the things that could be helpful would be to actually draw the electrons that are basic. Okay? We have the pi bond and we have the lone pair on the nitrogen. Which of those do you think is the most basic? The lone pair. Why the lone pair and not the pi bonds? Why the lone pair and not the pi bonds?
The pi bonds are in resonance with each other.
The pi bonds are in resonance. Okay, so we would expect the lone pair to be the more basic one. Can that lone pair do resonance? And this is a challenging question. Couldn't we just say do something like this? And if we look at the arrows, like, why not? Right? Nitrogen would have to become positive. But, I mean, if it's donating electrons, it should do that. So that double bond structure looks a little bit weird, right? Okay. That bond angle is supposed to be 180 because there's only two groups of electrons around that nitrogen. That's going to be a kind of stressed structure, so that could be questionable. Okay. Everybody's least favorite, particularly Mustafa's. I deserve it. Let's take a look at that pyridine structure on its side. And what we're going to do is look first at the pi bonds. Those pi bonds are due to the overlap of p orbitals. Yeah? Where's the lone pair on that nitrogen? It's in a perpendicular orbital. If it is in a perpendicular orbital, can it do resonance?
No.
No. That lone pair has no resonance. You could draw out the structures and be, yeah, that just looks awful, and accept that. The explanation is that it's in a perpendicular orbital. It can't do resonance. Okay? So we really just have a nitrogen holding a pair of electrons. Okay? If we move over to the other nitrogen, we got the suggestion that that one was what?
More basic.
More basic. Okay? And you said it's more basic because?
It's sp3.
That's not what you said, but let's go with that. We're looking at sp3 versus sp2. And if we're going to go based off of a hybridization argument, the sp2 is more electronegative than the sp3, which means what is it doing with the electrons? Holding them. And what does a base need to do? Donate them. So according to your argument with hybridization, pyrrole is more basic than pyridine, yeah? Okay. That's getting into the oh crap analysis. That's our hybridization effect. Is there something you should be evaluating before?
Everything else.
Yeah, everything else. Okay. That was a not so nice way of saying that, but yes. Okay. Charge, neither of them charge, so irrelevant. Atom effects, be it size or electronegativity, also irrelevant because they're both the same atom. Resonance. We looked at the resonance for pyridine. Did we look at the resonance for pyrrole? Is there resonance for pyrrole?
Yes.
What does that mean? We'll get to that in a second.
Those electrons are not always available.
Those electrons are less available because they are tied up in resonance, which means less basic. And our argument comes down to a resonance effect. Okay? You already knew that because you knew resonance. There's an extra layer on top of why pyrrole is actually not basic. Okay? What topic did we cover on whatever the last day was? Monday. great. We all remembered with great memories that we were talking about aromaticity. And we looked at aromaticity, we wanted to know how many electrons were in a conjugated pi system, a cyclic conjugated pi system. Is pyrrole cyclic? Yes, because it's a ring. Yes, it's cyclic. Is it a conjugated pi system? Can I show resonance? Yes. How many electrons are in that pi system? 6. If there are 6 pi electrons, it is aromatic, like benzene. Pyrrole is aromatic. Those electrons are what's making it aromatic. Benzene is incredibly stable due to it being aromatic. What does that mean about pyrrole? It's incredibly stable. The lone pair of electrons on that pyrrole are stuck in an aromatic structure and therefore will not share easily. That makes pyrrole very, very unbasic. In the pyridine is still also 6. Okay? But what makes the pyridine tricky is that what we're concerned about is this pair of electrons, which isn't part of the aromatic system, which is why those electrons are available to react. There are 6 pi electrons in pyridine due to the pi bonds there. The lone pair on the nitrogen isn't part of that system. Okay, so when we talked about counting the electrons on lone pair electrons on atoms in the ring, you can count 1 pair of electrons from an sp3 atom. The nitrogen in pyridine is sp2, can't count it. Okay, why can't you count it? Orthogonal orbitals. Okay, or perpendicular orbitals. Okay, so what we could go through and do is we could prove this by looking at acid-base chemistry and looking at the pKa's of the conjugate acids. If we take a look for pyrrole, the pKa is 0.4, meaning once we protonate the pyrrole, it is an exceptionally acidic structure. What does that mean about its conjugate base? It's a very weak base. When we look at pyridine, the pK isn't exceptionally acidic, okay, which means its base will be relatively stronger. Okay? So we can look at it through pKa's, or we can look at it based off of aromaticity and resonance and all that fun jazz. Make sense? I do want to take a quick second to reference backwards to a comment Alex made and then did not make again.
Oh yeah, it was on the test.
It was on the test with the nitrogen. That's true. It was on the test with the nitrogen, but not pyrrole. This nitrogen is sp3 hybridized, and I should now be using a hybridization effect to explain its acidity or basicity. Why is that nitrogen different than pyrrole? They're both sp3 hybridized. It's the conjugation. You have to see where the location of those pi bonds and that conjugation affects it. And so when it was on the exam, it wasn't set up in a system where it was conjugated. Okay? So the location of secondary functional groups makes a really big difference in your analysis, so you have to be careful with it. For instance, what functional group? Alcohol. Carboxylic acid. Okay? The chemistry drastically changes by just bringing in another functional group. So you have to watch out for that system or that stacking of functional groups. Kind of make sense? Okay. So, come back here. Foreshadowing. What would be the chemistry expected for this molecule? Right? Is it stable? No. Why not? Positive charge. Okay. How might it alleviate that positive charge? Taking electrons from somewhere. We could have a nucleophile. Whoa, I did not do that. Oh, Jiminy Christmas, internet. What does Jiminy Christmas mean? It means I'm cursing without cursing. That's what happens when you get a 3-year-old in America. Yeah, everything's locked up. Great. Okay, so I think I can get away with it here, and we'll see if it catches the internet back here in a second. But I believe what we had was this structure. So one suggestion was that a nucleophile with some form of electrons, let's not make it negative, could come in and share. Okay? That is a possibility. That is fair game. We are neutralizing that positive. Okay? There's another thing that could happen.
Elimination.
We could do an elimination. We could take the electrons from the hydrogen, or for that matter, the bromine. Okay? So we would end up with 2 possible results that could have come out of this. There's that new pi bond, bromine, or we could have ended with bromine H. Everybody see it? Which of those 2 products would we expect to be more likely? Purple or red?
Red.
What topic did we just cover? Begins with an A, and it doesn't end with whole. Aromaticity. I'll wait for that one to sink in. Geez, I didn't think it was going to be that bad. Aromaticity. What is the difference between our products or all of our structures? Do we have an aromatic structure in any one of those? The purple one is aromatic. Because it is aromatic, what does that mean to its energy? It is the most stable, which means that's the most likely route. Okay? And so what we need to do in our reactions with aromatic rings is to somehow get to this insanely charged state with that positive charge. And if we can achieve that, it's going to very quickly revert back to the aromatic structure. Okay? So that's what we're going to end up seeing in the next sequence. And let's see. Are you going to work with me yet? Cool. We're there. So, because we're short on time, I'm going to try my very best to actually pick up speed. And Rosie, thinking short on time today? No, short on time in the semester. We've got 3 class periods. Ideally, one of those is more of a review than talking about new content. Okay? So I need to cover like 40 slides in 2 classes. This is our big overarching summary of the new content. Okay? This covers pretty much everything in the next 2 chapters that you're responsible for. So one of those chapters is a big summary of all the reactions. That's the aromatic reactions, REAS, okay, as it's referenced. So you're responsible for each of those functional group or those reagents and what they would produce. There are some nuances and subtleties within those which we'll talk about, but for the most part, you just need to know the reagent does that thing. Kind of make sense? Okay. Some of those, there's some secondary chemistry, hence the second layer in blue. Okay? So that whole section in the top, I guess I could box that. Why not? All of this is, what are the 2 chapters? Was it 21, 22?
I think so.
Right.
20, I think it's
23 and
23.
22, 23. In red is 22. Everything else is 23. Okay? So in 22, it's just, here's what we do. We do these reactions where we start with a benzene and I do a substitution. I remove a hydrogen and I put on another group. Okay, that's it. So you just have to know those reagents and sometimes the inner subtleties of their reactions. Okay? So if you haven't been already, memorize reagents. This is an easy one to just throw down on note cards and just cram for the final test. Okay? The rest of these are what show up in the next chapter. Orange and purple, okay, are starting with a slightly different starting material. Okay? When we looked at 22, we're starting with benzene. They're all hydrogens. We move to 23, we have an X on there. It's not just benzene. It's something that's already connected to that benzene. Okay? So what we need to do is learn about how that thing affects the rest of the reaction. How does that change the reactivity of the hydrogens? That change then gets these, of course, secondary classifications. Activators, para-ortho, electron donating. Deactivators, meta, electron withdrawing. So it's telling you where your substitution is going to happen. Right? What defines electron donating? If atom X has more electrons than hydrogen atom. What atom has more electrons than a hydrogen atom? All of them. Every single atom has more electrons than a hydrogen atom. Okay? Which might then cause an issue when we move to the next one. Deactivators are electron withdrawing. This is atom X, has, copy-paste, less electrons than a hydrogen atom. Well, what atoms have less electrons than a hydrogen atom?
Hydrogen ion.
Okay? We might say none of them. Well, hydrogen ion has less, but if I have a hydrogen ion, it's not connected to it. Okay? So how could I possibly have an atom X, and for the sake of space, I'm going to do a slight rotation here, and I'm going to put atom X over here. How could this atom X have less electrons than a hydrogen atom? How many electrons does a hydrogen atom have? 1. So how do I have less electrons than 1 electron? What would happen to my atom?
It's floating on its own.
Nope.
And it's probably going to react to the first thing in the
Nope. What would happen if I have less than 1 electron? It would be positive. So if I look at atom X and atom X is positive, guess what? It has less electrons than hydrogen. We're now looking at a deactivator. The classic group for that, and this is where sometimes people might freak out, would be NO2. NO2 is electron withdrawing, but doesn't nitrogen have more electrons than hydrogen? It does. Look at the Lewis structure for NO2.
So you want to be valence electrons and not electrons.
The nitrogen is formally positive. By definition, it has less electrons than hydrogen because a hydrogen has 1. Nitrogen has an imbalance, and that's why it's positive. So if we can draw a structure that has a positive charge at some stage on the atom directly connected to the ring, that now classifies as an electron withdrawing group. Okay? The last 3 reactions are kind of weird oddities and usually one-offs when it comes to the ACS, hence my kind of segregation of my opinions behind them. The Birch reduction we've already talked about. It's sodium in the presence of ammonia. Where do we see that reagent show up before?
Redox.
Yeah, it was in reduction and oxidation. Technically, it was reduction. What was it used to do? And don't tell me reduce. Something about trans. Yeah, that's good. Something about trans. When do I see trans? When I have a pi bond. When I'm reducing a triple bond to a double bond. That's when I would use sodium and ammonia. And that one was a neat reagent because it ends in the trans alkene, where most of our reductions end with cis. Okay? So that's why that reagent was super important. That's where we saw it show up. It shows up again with benzenes. Sodium is so reactive that it will force benzene to react. Yes, it forces it to react weirdly. We'll talk about the dynamics behind that. We do encounter 2 other mechanisms known as the nucleophilic aromatic substitution. Okay? Notice we're still doing a substitution reaction. This one fits a little bit better with our patterns because we have a leaving group and we have a nucleophile coming on. So that might fit our better patterns, but how many times do we see substitution on benzyl halides? or benzene halides? We don't. It doesn't happen. Okay? So we need very special chemistry for that to work. The special chemistry, you need a really good nucleophile, hydroxide or amide. Those are the only ones that would be allowed to happen. On top of that, we need sometimes a little bit of heat. We can also use withdrawing groups, okay, to help polarize the structure and allow it to react. The elimination addition mechanism is all sorts of fun on its own because we end up with two products. The reason why we talk about this one, it's neat because we form a triple bond in the ring. Triple bond. Think about that one for a little bit. It's kind of cool. Okay? So those are all of the reactions. What we're going to try and talk through in 2 lectures, which will probably skip into 2.5, is all of that. Okay? So let's push a little bit. Electrophilic aromatic substitution. For those of you in lab, you've got a precursor on this, so you should be able to help out. Electrophilic means I have something that is positively charged. Okay? I also have an aromatic. My classic aromatic is benzene. Would I expect the benzene to also be the electrophile? When you look at benzene, does it look inherently positive? No. If anything, what does it look? Okay, it's always going to look neutral. You're saying more like a nucleophile because we have lots of pi electrons. So our benzene is going to act as our nucleophile, our electrophile is our electrophile. Okay, some other positive thing. The next word in this is substitution, which implies we're doing a chemical reaction. That electrophile must somehow substitute for something in the benzene. Well, what's in the benzene? Hydrogen and carbon. What's going to be the easiest thing to substitute? Hydrogen. So, let's try that a little better. We've now done our substitution. The name gives us those patterns as long as we apply the name to what we know about our chemistries. Okay? How is this going to work? Let's come up with a generic mechanism. We said the benzene acted as a nucleophile, which means the pi electrons need to attack the electrophile. Okay? The result, that electrophile is going to be attached to the benzene structure, and I will have a carbocation on it. Okay? Is that a particularly stable structure? No. What is the most likely thing that it could do right now? We could take the electrons away from the electrophile and go right back to where we started. Okay? Or, I don't even want to look at the hydrogen yet.
Double bond.
What's that?
Use the double bond.
Use the double bond, also known as resonance. These resonance structures are the reason I think EAS is easy. Because if you do resonance, you have the answers. Everything we're going to discuss is resonance. Okay? And you will see questions asking about these intermediate resonance structures. So if you are comfortable with resonance, which you should be, because I've told you to keep working on it, this should be an easy unit. Okay? Now what happens? Now I can remove the hydrogen. And what's the result? I reform the aromatic ring, I kick off H+, and I've got my electrophile now attached to the structure. These structures down here are known as sigma intermediates because that blue carbon only has sigma bonds. Okay? So in our nucleophilic addition eliminations, we had to go through a tetrahedral intermediate. Okay? You will see questions based off of that. Just like that, you will see questions based off of these sigma intermediates. So you have to be familiar with how to draw them. If you don't know how to draw them, that's a problem. Okay? And ultimately, the only reason you don't know how to draw them is because you thought you could do resonance structures in your head. Which if you can, that's good. You should be able to do that by now. And you shouldn't have to show those. Okay? That will drastically increase your speed on the final. Okay? So, we could go through and look at a much prettier version of it. Ta-da! That's literally it. It's a pretty version of it, though. No, actually, I can't go back. This literally everything I wrote up here, I just wrote by hand. This is just a pretty version of it. Did you want colors?
Yes.
Okay.
Obviously, that's what
Okay. These were red. I remember all that. That was red. That's about all I remember. The sigma complexes, because of that carbon only has sigma bonds. Sorry, I didn't see anybody typically color coding, but I didn't see you every day doing it. I apologize.
You don't recognize these?
I see it now. Give me.
How come you
I'm
can't go
colorblind,
back?
actually. Don't you feel bad now for insulting me? Because I'm colorblind.
No. How come you can't go back?
It's how it's established in the slide. It's how I advanced. When I advance slides, it deletes whatever I wrote. Okay, so you're not drawing anymore? Can I go on now? Okay. Sorry. Okay, so speeding the reaction. We can make our electrophile more electrophilic, which means we need a more positive electrophile. Okay, so electrophiles. Which of those do you think is the most electrophilic? Well, an electrophile is positive. Which of those is the most positive? The middle one. There's a formal positive charge on it. That one's exceptionally electrophilic. Which one's the next most? The carbonyl carbon. Okay, why? We have a resonance and we have a di-induction, double induction effect, making that carbon very positive. Okay, the last one would be our bromine. How could I make that bromine more electrophilic? Well, to make it more electrophilic, I would need to get this other bromine to start pulling the electrons away. Okay? For that bromine to pull electrons away, there has to be something nearby that bromine could potentially give its electrons to. That something nearby could be great if it was an H+. If I run it under acidic conditions, okay, that bromine can start to coordinate with H+, making the other bromine very positive. Okay? The typical example is to use, those of you in lab, acetic acid. Okay? Acetic acid works very well to polarize that. Okay? I could also use other atoms. What other atoms typically carry a positive? Metallica. What was that? Metals. Making a metal reference, right? Iron. If I attach that iron to some bromines, FeBr3, that iron is very positive, so what can happen is our bromine can polarize, bond to the iron, freeing up the other bromine to be positive. Okay? The nitro I don't really need to worry about because it's already positive. How about the last one? How could I polarize that structure more? I could protonate the oxygen by adding an acid. Ta-da! That works. Okay? Or, as Milana suggested, I could use something like aluminum chloride. Notice aluminum is also a metal. What is special about the aluminum? Aluminum, according to its octet, is happy with 6 electrons, which means there's literally an empty p orbital to dump electrons in. Where do those electrons come from? Our chlorine. Okay? So what we're talking about doing is adding acids, or what is the aluminum acting at, or acting as, or the iron acting as? What did they do?
Accept electrons.
They accepted electrons. What species accepts electrons? Electrophiles. But if they were electrophiles, they would ruin our reaction. So we don't want to call them electrophiles. What other species accept electrons? Acids. They're doing the exact same thing as the H+ is doing. So what we are adding as a catalyst is an acid catalyst. In this case, we don't want to narrow our definition to Bronsted-Lowry. We'll reference it as the entire category, which means Lewis acid catalysts. So with most of our electrophiles, we're almost always adding some kind of Lewis acid catalyst behind it. As a catalyst, it is not strictly necessary for you to be able to zero in on the presence of that. What you need to zero in on is the presence of the electrophile. That's going to help you predict your products. Make sense? Okay. Can I go on? So, if we use chlorine, we can use iron trichloride. What ends up happening is that chlorine will coordinate with the iron. That middle chlorine starts to be unhappy, so it steals electrons from the last chlorine. That frees up Cl+. So the active electrophile is a chloronium ion, I guess? A positive chlorine. Okay? Could we get a positive carbon? How could I get a positive carbon? Let's try it that way. For it to be positive, what must it be connected to? Something. I don't quite accept negative. I know where you're going with that, but more electronegative. Okay? Like a halogen. Halogens would be an awesome selection for that because I'm now looking at an alkyl halide, which means the carbon can only act as an electrophile. It reduces the amount of chemistry. If I threw on an oxygen, I now have an alcohol, which has a variety of extra chemistries. Okay? So I could throw on a halogen. Let's pick chloride for an example. This now gives me a pretty decent electrophile. That decent electrophile isn't good enough to react with benzene because benzene's very stable. I need to make that more positive. How can I make that more positive? What must this chlorine do? Leave. Okay? For it to leave, though, it must be made extra stable. What could I add to make that chloride extra stable? Literally what we just talked about, yeah. I could add aluminum trichloride. That aluminum with that empty orbital will accept the electrons from our other chlorine, polarizing that structure further so that I now get a super positive carbon. How could I get this super positive carbon? Okay, right now, is it positive? No, the oxygen's positive. Why isn't the oxygen colored in red to be the electrophile?
You can't accept more electrons.
Could the oxygen accept more electrons right now? If we actually complete our Lewis structure, it has a pair of electrons. It can't accept more electrons. So the positive is a good place to search for it. My reactivity needs to be darn close to that. And in particular, what I can do is see the oxygen can't accept more electrons, but what it could do is pull electrons from the carbon, drawing a potential resonance structure. Which of those structures is better? You said top. You said bottom. Why do you want to say bottom?
The carbon can sustain a positive charge better than oxygen can.
Okay, so the explanation for the bottom one is the carbon can sustain a positive charge better than oxygen. Ultimately, you're saying oxygen is more electronegative than carbon. Cool. Why are you saying the top is better? No, not because of the triple bond necessarily. Why is the top one more stable than the bottom?
Carbon has 4 bonds.
Better. Give me some better word choice.
Octets.
Carbon has its octet. The top one is your best Lewis structure. As the best Lewis structure, is that where my chemistry is? No, what do I have to do? Look at the first worst. The first worst shows me where the chemistry is. And I would agree with you, Rob. I want to draw this because now I see the chemistry and how I know it reacts. But if I'm asked which one's the better one, I have to say this top one. Okay? And yes, that sucks, but that's the rule. Okay? So where did I get this structure from? Does that help give you a hint? How did I get this positive carbon?
Remove the chlorine.
Removed the chlorine. How should I get this positive carbon?
Remove the chlorine.
Let's remove a chlorine. Yes. Okay. How could I help polarize and get that chlorine to come off? Okay. The exact same Lewis acid catalyst. Okay. So what we're looking at is how do these charges kind of replicate and move through and finding those sites of reactivity. Okay? These last two reactions are both reacting an electrophilic carbon. Okay, so commonalities. And they're using the same Lewis acid catalyst, aluminum trichloride. Because of that, they get grouped after the central chemistry that they were founded by. That's Friedel-Crafts. Okay, so the middle one is a Friedel-Crafts alkylation. Alkylation. The bottom one is a Friedel-Crafts acylation, because you're adding that carbonyl and carbon group. Okay, so you'll see reference to those terms. We can throw them up there. Nope. Yep. Come on. Give me the pen. Top one is an alkylation. And the bottom one is an acylation. Okay, we have some notes here about their reactivities. Okay, for an alkylation, you need an active nucleophile. We don't really know an active nucleophile yet, so an active benzene ring, because we haven't looked at substituted benzenes. Okay, but it is going to show up. Why do I need a more active nucleophile with the carbon one, whereas the acyl doesn't need to be an active ring? How stable is a carbon positive all on its own? It's awful, okay? Which means its concentration is very, very low. So to get the alkylation to work, I need to have a nucleophile that will react with it immediately. I need an active nucleophile. When I move to the acylation, I still have a positive carbon, but that positive carbon is resonance stabilized, which means it can exist for longer in solution, which means I can take my time with a less active ring. Kind of make sense? Okay, so that's a big difference between those two reagents. Okay, some limitations on the Friedel-Crafts alkylations. If we were to go through and predict our product here, what would we expect? Okay, right? We got the benzene ring. We're doing the substitution, so we're just going to pull a hydrogen. All the hydrogens are the same, so I'm just going to delete a hydrogen. There's my electrophilic carbon, right? So I would expect... Yeah, right? Don't get it. What do I get instead? Why? the carbocation that we formed was a primary carbocation. Primary carbocations are inherently unstable, so it undergoes a hydride shift to form a more stable carbocation. That more stable carbocation is now allowed to react with the benzene. So a big problem with our alkylations is rearrangements. Okay? We are forming carbocations. So if you're going to do an alkylation, we want to be very cognizant of the fact that we could get rearrangements, right? And be careful with what reagents you pick. Make sense? Okay. I'm surprised how quickly at least a few of you picked that up. That was awesome. Okay? So, there we go. So, see, nice drawing as opposed to crummy colored drawings by me. Okay, so they're susceptible to our rearrangements. Okay, what is expected of this alkylation? Okay, so that's a decent question. So let's fix that real quickly. That's an artifact of me not having that structure easily available. What might we expect as the product here? Two benzene rings stuck together, right? What do we get?
Probably not that.
Probably not that. What we get is no reaction.
You can't stabilize the carbocation.
Remember back when we talked about SN1 and SN2 in Unit 1 of first semester? This structure can't form the carbocation. That doesn't happen. So there is a hybridization effect when we're looking at our Friedel-Crafts alkylations. We have to start with an sp3 carbon. Okay? And I don't think I have anything pretty on that. No, I don't. Okay? So they don't work. So it has to start as an sp3 carbon. Okay? So that's our last big restriction on it. Again, we'll come back to that active versus less active in the next chapter. So, more electrophiles. Okay? These are electrophiles with Bronsted-Lowry acids. So we said NO2 was an electrophile. Okay? Where do I get that from? Okay? I would need a positive nitrogen. Okay? Well, just like we did with the CO2 or the carbons, right? We could back this off and say negative, positive. I would need to attach something there, right? What could I attach there?
Halogen.
We could throw in a halogen. How many times have we seen that kind of bond show up? Yeah, we haven't. That's a pretty dodgy bond. Okay? That might actually be explosive. Okay? So that's not particularly safe. But we do want a leaving group, right? We would want something there that could work. With the carbons, we said we didn't want OH because the OH could act as multiple things because that would be an alcohol. Is it necessarily an alcohol if I throw it on there now?
No.
Might not be. What structure did I just show? As a hint, it starts with H. You know where the answer is. HNO3 is a strong acid. Okay? It wants to ditch this hydrogen. If it ditches that hydrogen, is that getting us to our NO2? No. Okay? So we now have a problem. We're saying, well, now maybe we can't do it. Okay? You ever heard that statement, there's always somebody smarter than you? Right? There's always an acid stronger. What's the acid that's stronger than nitric acid? Sulfuric acid. And sulfuric acid is so strong that what can it do? It can force the strong acid, nitric acid, to act as a base, thereby turning this OH bad leaving group into a good leaving group that can pop off the structure, leaving us with the NO2+. Okay? So this reaction is a neat one, okay, and it is commonly pushed at least I've pushed at it in other classes, because you're taking what we've always taught you as a strong acid and we're making it act as a base. Okay, so that is a common kind of question that can pop up because it goes against the grain of what you've been told to memorize. Does that make sense? Okay. But the end result is that we form our strong electrophile. So we're taking H2SO4, nitric acid, sulfuric and nitric acid, we put them together, we get NO2. Okay, there's our electrophile. Okay. We could also do this with just sulfuric acid. I can take concentrated sulfuric acid and it can react with itself, forming a sulfur electrophile. Okay. What that will end up doing, whoops. So I guess I added that in there and then didn't give me a nice red box. Is I now have a sulfur as an electrophile. Okay? What makes that reaction super, super important? It's reversible. Okay? Meaning if I want to get a sulfur or this sulfate structure off of a benzene ring, what can I add? Water. Water will now attack the sulfur, making it a good leaving group so that it can leave and we can put a hydrogen back on the structure. Okay? So the sulfate one shows up every so often. Usually what it's being used for is a blocking group. We've talked about protecting groups before. The sulfate isn't getting used as a protecting group per se. It's getting used as a blocking group. It prevents the reaction from happening at that site, that you can then remove it and re-expose that site again. Okay? Kind of like a protecting group, but slightly different. Okay? Last one, this is another carbon electrophile. Okay? The reason why we talk about this one is that it's slightly different than our Friedel-Crafts. In the Friedel-Crafts, we added a Lewis acid catalyst. We're talking about Bronsted-Lowry acid catalysts. I can start with an alkene and add a strong acid. What happens? It protonates, forming an electrophile. If the only nucleophile in solution is benzene, guess what's the nucleophile? Well, benzene. And I can do the EAS reaction as well. That one tends to be less common, okay, but it can show up. If we look at the names for these, we've got nitration, sulfonation, and alkylation. Okay. Some special kind of, did I fix this slide? Yeah, maybe I did. Kind of nomenclature terms. We had the allylic position, which was one carbon away from a pi bond. The benzylic position is very similar in chemistry. Okay, so we get some bizarre stuff happening at that point because we get a lot of resonance stabilization within the ring structure. Okay? So when you're asked to evaluate reactivity of a benzylic position, what they're talking about is one carbon away from the benzene. So if you've heard reference to a benzyl group, okay, if I want to look at benzyl chloride is not that. That's chlorobenzene. Okay? Or phenyl chloride. If I wanted to reference benzyl chloride, I need that extra carbon away from the ring. Now I can put on a chloride. That structure is benzyl chloride.
I still think that's weird.
I agree with you. I think it's irritating. Right? What's that? The allylic is up at the top. top left, the allylic is 1 carbon removed from the pi bond. So they're roughly the same thing. It's a carbon 1 away from a pi bond. But if it's an alkene versus an aromatic, their chemistries are slightly different, so they get different names. So allylic and benzylic. Okay? And since we're on that topic, what if you were the carbon of an alkene? That one's vinylic. Okay. Kind of nomenclature things, probably not all that important. Okay. But what is important to do is to recognize that resonance. Okay. And that we get new and interesting, bizarre chemistries. Okay. One of those chemistries is that we can get this substitution reaction to happen very, very fast. Okay. Under SN1 conditions, because a lot of resonance stabilization. Okay. The more important thing, though, is not that one, would be this. Okay, this is the new chemistry of the benzylic position. Take a look. I've got my benzene, and I've got this long carbon chain attached to it. And what I'm going to throw at it is chromic acid, or permanganate. We'll do the same thing. Okay, they're both strong oxidizing agents, and they'll cremate these. I don't know. Okay, and what they will do is they will oxidize the benzylic position to its fullest extent. Okay, does anybody have any itching questions by looking at that reaction?
Where did the carbons go?
Where the hell do the rest of the carbons go? I don't know. Okay. Every semester I look at it and go, I need to look it up and try and figure it out. And you have to dig a lot to figure out where those carbons went. Okay. And so I just haven't seen an explanation of it. Okay, what you need to know, though, you throw an oxidizing agent at a benzene structure that has a benzylic position, it activates, okay, or it oxidizes. To oxidize, what did you remove? Hydrogens, which brings in the key piece of information for this. It's not just that you have a benzylic position, it's that you have a benzylic hydrogen. How many hydrogens do you need? 1. As soon as you have one benzylic position, it's effectively the camel's head underneath the tent. The entire thing will oxidize out. Okay? So as long as you have that hydrogen, the whole thing goes, and you end at benzoic acid. Okay? What happens if you don't have a hydrogen at the benzylic position? It doesn't oxidize. It just doesn't work. Okay? So,
What if you have, is there a difference if you have 1 or if you have 2 hydrogens, or is it just you need only 1?
you only need 1 and you go to benzoic acid. Yeah, and what happens to the other carbons? Stuff. That's about all you need to know. Other oxidizing agents, I've seen permanganate used instead. Okay? So, if I take toluene and add, ta-da, permanganate, here's our other oxidizing agent, what do I get? What would happen? It's going to turn into benzoic acid. I have a benzylic hydrogen, right? I have at least 1 there. Okay, because I have that hydrogen, what happens? It's going to go to make benzoic acid. How about the next one? An alkyl benzene. In this case, what is that? Sec-butyl benzene. Is there a hydrogen there?
Yep.
Yeah, so what happens? Benzoic acid. Okay, how about the next one? Is there a hydrogen there? Yeah, what happens? Benzoic acid. Okay, the alkynyl benzene. This one's a little bit interesting. Do we have a hydrogen there? No, but what we do have is the triple bond. And what does the triple bond do in the presence of permanganate? Oxidative cleavage. So it goes under the same mechanisms that we've already seen. Okay, so it's still going to end at benzoic acid. That one, you should be able to tell me the other piece. The other piece would be CO2. We move to the next one. There's no hydrogen, but the first step of our oxidation would be to replace the hydrogen with oxygen. Do I have an oxygen there? Yep, which means benzoic acid. I can finish it the rest of the way. That ketone is effectively just an intermediate along the way. So the ketone will still oxidize down to benzoic acid. So every single one of these will go all the way down to benzoic acid. Kind of, sort of? Okay. For those of you that want a mechanism, me too. Aromatic amines. Okay? We've now talked about all of the reagents that put things onto, well, through an EAS mechanism that will put a substituent onto a benzene ring. We've talked about all of them. Okay? There aren't any more hiding somewhere. In that process, did we talk about putting on an NH2? No. Did we talk about putting on a nitrogen? Yeah, we did. Okay? How do I get an NH2 on the structure? How do I put on the nitrogen? HNO3, H2SO4, and what do we get? I would get NO2. What do I need to have happen to go from O2 to H2? I need a reduction. Do I know any reducing agents? Yep. So what can I do? Throw a reducing agent at it. And that'll reduce that second step. That's how we're getting the NH2 on. Not quite through an EAS mechanism, because we're still going through NO2, but what we end up doing is some type of reduction. Okay? Notice I'm saying some type of reduction. How many different reducing agents are there? Lots. Lots and lots. So you can see a whole variety of reducing agents. The H2 in palladium is one you've already seen. HCl in iron you haven't seen. Okay? It is a dissolved metal reduction, kind of like our words, Clemenson. Okay? That same kind of process. Okay? We don't need to know the mechanism, but we do need to know that it's possible to get there. Okay? So we put on the nitro, and then we can do a reduction. That gets us our NH2. Okay? What makes the NH2 interesting is actually the next part. Okay? I can take sodium nitrite in the presence of an acid at low temperatures, and I can react that with the aniline. Okay? How might I expect this reaction to go? So the first thing we should do would be to draw out what sodium NO2 looks like. What would the charge be on the NO2? It would be a -1. So is this the same thing as the NO2 we had before? No, because the NO2 we talked about before was positively charged. So this is a different reagent. If we go through and attempt to draw this out, nitrogen 5, oxygen 6 times 2 plus 1 because of the charge, 12 and 6, 18, yeah? Nitrogen, oxygen, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. What did I get? That's 16, 18. Do I have octets on all my atoms? No, good job. I'm missing it on the nitrogen. Drop in that lone pair, that bond. And I would now have my NO2 minus. For those of you going, that was really fast, Mike. That was impressive. I'm glad I don't have to do that. Yes, you do. Yes. Okay. The test covers all of OChem. Lewis structure was day one. You need to be able to draw a Lewis structure and know how many bonds there are, how many electrons, where are the charges, all of that fun jazz. Okay? And you should be able to do the Lewis structure stuff insanely fast. Okay? Last thing, negative on the oxygen. Okay? So when I look at that, and I look at my aniline, and I look at my other reagents, what do I see as reactivity? I see that negative charge screaming at me. Yep, negative charge, which means I would need to find a positive somewhere. And because we're studying EAS, I know that the benzene ring is going to act as a nucleophile, which is not positive, damn it. So instead of reflexing, saying, oh, it must be the ring, I got to use the ring, look at your other reagents. HBr is a strong acid, meaning H+. This mechanism is really neat and really long. Like really long. I'm not going to draw it all. Okay? But what we'll do is try and highlight where those reactivities fall. The very first thing that comes out of this reaction is that that acid will protonate our sodium nitrite. And we will now have a hydrogen on there. Okay? Does that look familiar at all? I mean, we've got some kind of atom double bonded to an oxygen with some kind of leaving group. Oh, dang, I gave too much away. Right? That nitrogen is a good electrophile. It could be made better if, say, we were able to protonate that oxygen again. But to protonate that oxygen, I would need to be in what kind of environment? An acidic environment. Okay? Which means that nitrogen is now a very good electrophile. Where's the next best nucleophile? We could jump to the ring, or there's lone pairs on the nitrogen of our aniline. That nitrogen comes through and attacks the other nitrogen, kicks out our leaving group. Okay? And maybe some of you can propagate this out in your head and see how nasty this is going to get. We'd have a positive nitrogen, right? So what happens? Deprotonate, it's now neutral. That's not particularly stable. Good thing I'm in an acidic environment, and what could happen? I protonate that oxygen. That would then start to pull electrons away from that first nitrogen, right? But then it would miss its octet. It's a good thing there's another nitrogen to share electrons. You're like, dude, Mike, just stop. This is already too painful. I know. It's okay. Don't worry, it gets worse. Oh, that nitrogen's positive again. That's bad. I know. Let's get rid of that hydrogen. Still under acidic environment. So let's get rid of one of those lone pairs and put on another hydrogen. Right? But then that oxygen would be positive, so what would it want to do? Leave. But then that nitrogen would be F'd, so what does it do? Takes electrons from the other thing. End result, I'll draw it in black and then I'll delete everything. I intentionally tried to make this messy so that you didn't try and copy this mechanism down, just for the record. Okay, and you end up what is known as the Benzenediazonium. Okay. Does anybody want to copy more of that down, or are you just okay with just accepting generally what it is?
I'm good.
Okay, the textbook definitely has a nicer image, and I might have it hidden underneath. I don't think I do because it's long. Go away. No, stop showing all that. Here we go. This starts it. Okay, so 1, 2, 3, 4, 5, 6. Notice we're at step 6, and I don't even have a double bond between the nitrogens yet. 7, 8, 9, 10, 11. Okay? We've got 11 steps. Most of them are acid-base steps. Okay? So it is really long. The important piece is to recognize what we end with, okay, which is that Benzenediazonium at the bottom. So I'm going to erase everything except for that structure at the bottom and let that structure kind of sink in a little bit. So look at it, think about it, evaluate it, tell me what you see.
Could act as either nucleophile or electrophile.
What's that?
Could act as either nucleophile or electrophile.
How so?
We've got the lone pair on one nitrogen and positive charge on the other.
There is a positive charge on that nitrogen. Could it accept more electrons? No, it has its octet satisfied. So we don't have an electrophile in that nitrogen. Could that tail end nitrogen potentially donate its electrons out? Yes, but then if it did, it would become positive, and what would it need to do? Steal electrons from
The guy that doesn't have.
the atom that doesn't have any electrons. So really, neither of those nitrogens are particularly reactive as a nucleophile or an electrophile. But it is a positive nitrogen. And I like where you went. You said, okay, positive nitrogen, chemistry must be nearby, and so you looked at this other atom. Is there another atom? What's the special issue with that carbon?
It has a pi bond that could resonate.
There is the potential for a resonance, yes. Does that nitrogen want to be positive?
No.
No. What might it do? Steal electrons from the carbon. If it did so, what does it make? Also known as nitrogen gas. That is an exceptionally good leaving group. Okay? The problem with that leaving group, though, is what does it leave behind? A positive carbon, which we all know doesn't happen. Okay? So, of course, somebody got to attach their name to it, and that's where we get the Sandmeyer reactions. Okay? So while that is a great leaving group, it doesn't leave a good carbocation. So we need some kind of catalyst to temporarily stabilize that to allow for that reaction to happen. And that's what I skipped up here and above. Okay? So if we look all the way up at that top, once I've formed the Benzenediazonium, come on, pen. I do have a really good leaving group out here, but I have a really bad substrate. So this is where we can add a catalyst like copper. Copper metal will help coordinate those two pieces. What charge was the carbon? Positive, because our nitrogen would leave with the electrons, which means the counter that we're adding in there needs to be negative. So copper bromide. The copper helps to kind of coordinate and temporarily stabilize that carbon during the transition of the nitrogen leaving and the bromine coming in. Okay? So we end up doing an interesting substitution reaction that can put a halogen on. Couldn't I put a halogen on the ring right away? I mean, to get to the NH2, what did I have to do? I reacted benzene with nitric acid and sulfuric acid. Then I reduced it. Then I did this irritating sodium nitrite bromine billion-step mechanism. And then I put a bromine on. Or I could have just said, take benzene and bromine. Br2 and FeBr3 right out of the gate. Ta-da! Done. So why do we need this sequence of reagents? Because maybe we don't start with benzene. Maybe we start with the aniline. That's what we have to deal with. Okay? And that's where synthesis comes into play, why these pieces are showing up. These are tools that you could use. Okay? There may be alternative methods to get through this where you can avoid that. Where it becomes more important is not with the placement of the bromine, but is our other sequence of reagents known for our Sandmeyer reactions. I could put on chlorine or bromine. We've already done those. I could put on a nitrile. We haven't seen that one. That's now a new interesting step. I don't have a way of putting on a nitrile. Okay? Now I can do it. I can put on iodine. I can put on fluoride. Okay? I can put on an OH, which we also haven't been able to do yet. Okay? Or, this is super exciting, I can put on hydrogen, meaning
You can undo all.
I can undo everything that I did. Woohoo! Okay? Why would I undo it? Again, it depends where you're starting that process. You may decide that you need to undo it. Okay? But all of those are now kind of an extra layer on top of it. What I would bother to memorize is not all of those reagents. What I would memorize, sodium nitrite and the aniline and the NH2. If I see that sequence, I know whatever's going to happen next, find my negative, put it on the structure. Could be copper bromide. Okay? It could be copper nitrile. Okay? So what I'm doing is not memorizing what specific reagent is there, but recognizing the power of the Benzenediazonium as a really good leaving group that could potentially run this reaction. Does that make sense? Yes?
What about the phosphorus? Wouldn't that hydrogen be positive?
This is where you have to be careful with the mechanism. And this isn't even phosphite, because phosphite is PO3. This reagent, the phosphorus, is doing some nasty stuff with electron transfers, facilitating that reaction. So I don't think it's actually being added as H+. Okay? So there's all that fun mechanism stuff. Woohoo! And you know what's exciting about that? Chapter 22 is done. Or 21. Whatever it is. Yay! Okay? So there's our big summary of all of our reactions, or most of them. I didn't include the Sandmeyer up there. Be cautious of your sneaky undersided chemistry. Acid-base reactions, substituent conversions, alkylations, acylations. Okay? So those were the kind of red flag systems that you could encounter. Make sense? Okay. No. Okay. If we want practice about it, we can do that quiz later. Okay? So changing the rate for a nucleophile. The nucleophile becomes inherently harder to change the rate of. If I want to speed up the reaction from benzene, that benzene structure needs more electrons. Where can I put more electrons in this structure? Not anywhere. Because if I placed more electrons in there, what have I done? I've violated octet. Okay? So we can't speed the rate of the reaction by adding a nucleophile catalyst, for the most part. There are exceptions to that, but that's not where our primary driver is. So the primary driver on changing the rate of our reaction on the nucleophile side is actually changing the nucleophile. And in that change, what we're going to go through and do is, instead of having a hydrogen all the way around, we're going to put on an atom X. Okay, a generic atom X. I don't care what that is. X could have 50 other things after it. Those 50 other things after it have little to no effect on the reactivity of the ring. So when we're talking about the nucleophile chemistry, I care about atom X. What is the atom connected to the ring, and what are its properties? Kind of make sense? Okay. So in that discussion, there's really only two categories that we can place atom X. It can be atom X up top, where it has more electrons than our hydrogen. Or it can be the atom X on the bottom, where it has less electrons than hydrogen. How is that going to affect the reactivity? Well, when we had the benzene, which pi bond did we react? Red, green, or purple? It didn't matter, because they were all the same. If we now go up and look at the top, let's see if I can maintain the color pattern. Red, green, or purple. Are they all the same? No. Now there's a difference. So now I have to be careful with which pi bond I react. How would I know where that chemistry was? What's the reactive atom in that structure? In this red box that I'm now boxing heavily. The carbon. It's not the oxygen. Why not? It can accept electrons. Rob, did you like that drawing? No, you thought it sucked. Yeah, I don't think you used those words. Okay. You liked instead that one, right? What was that structure we just drew? A resonance structure. So if I want to predict how atom X is going to affect the reaction, what should I try and do? I should draw my resonance structures. Okay? Please do that over the break. So that when Monday comes back, we can just look at those structures, evaluate what they mean, and how that's going to affect our reaction moving forward. Does that make sense? Okay. With that, I'm going to go ahead and stop.